Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 19th, 2026, about 5 days ago. It introduces a new dataset called CORPUS and finds that modeling human intervention patterns yields an over 60% improvement in prediction accuracy compared to base language models. The paper is titled Modeling Distinct Human Interaction in Web Agents. And as we'll see later, the results are really impressive, with significant implications for building agents that collaborate effectively with users. Alright, Figure 1 outlines the entire research pipeline, starting with the problem in Step 1, where agents lack awareness of human intent. Originally, because standard agents didn't know when a human might intervene, users had to constantly watch them or deal with rigid timeouts. So in Step 2, the authors created CORPUS, collecting 400 real user trajectories to train a model that learns these specific intervention patterns. Finally, Step 3 illustrates the proposed solution, an intervention-aware agent that queries a prediction model before acting, which leads to fewer interruptions and better timing. Well, simply predicting whether an intervention happens isn't enough. Timing matters, so Figure 2 introduces the perfect timing score, or PTS. The timeline here shows a ground truth intervention at Step 6, but the model falsely predicts it earlier at Steps 2 and 4. To account for this, the metric measures the temporal distance between those false alarms and the true need for help. It then applies a penalty based on that squared distance, ensuring that interrupting the user way too early is penalized more heavily than a near miss. So to put that metric to work, the researchers curated a specific set of activities. Table 1 details the 10 standard tasks selected from the Mind2Web benchmark. These cover diverse domains like travel, service, and shopping, targeting popular websites such as United or GameStop. The rightmost column lists the specific prompts, like finding a flight with a budget or checking a trade in value. By keeping these tasks fixed, the authors ensure that any variation in the data comes from the user's interaction style, not the difficulty of the task itself. Okay, while the previous table defined the tasks, Table 3 now presents the actual interaction statistics collected in the CORPUS. It compares standard tasks against freeform ones, revealing a key difference in user behavior. Specifically, the intervention intensity is higher for standard tasks at roughly 22% versus 16% for freeform scenarios. This suggests users step in more often when facing rigid constraints. The step counts and timing columns support this, showing that standard sessions are generally longer, averaging about 117 seconds compared to 86 for user-driven goals. So, Figure 3 visualizes these interaction patterns by clustering users into 4 archetypes using principal component analysis. The scatter plot on the left maps users based on how often they intervene and whether they return control. At the top, the takeover group in pink steps in late and keeps control to finish the task. Below them, the hands-on users in orange frequently alternate actions with the agent. Finally, we see hands-off users who rarely intervene, and the collaborative group in green who make small corrections and then hand control back. Alright, moving from user patterns to prediction, Table 4 benchmarks how well different models anticipate these interventions. First, the baselines reveal a heavy class imbalance. The always-no intervention strategy gets 85% accuracy simply because most steps don't need help, but it scores a 0 on the perfect timing score. Among the closed-source models, even powerful engines like GPT-4o struggle to time things right, often remaining too conservative. In contrast, the fine-tuned open-source models steal the show. The author's Gemma 27b achieves a perfect timing score of 0.303, effectively beating the proprietary giants by learning the specific temporal dynamics. Well, Table 4 showed the models could predict interventions, but Figure 6 asks if users actually care. Here, the researchers deployed their model in a live agent called PlowPilot and compared it to the baseline CowPilot using a 7-point Likert scale. The bar chart on the left tracks satisfaction across 6 dimensions, such as whether the user felt in control or if the agent aligned with their preferences. In every single category, the gray bars for PlowPilot exceed the blue baseline bars. This consistent gap translates to a 26.5% increase in overall usefulness, confirming that an agent that knows when to pause is significantly more effective. Wrapping up, the big lesson is that effective autonomy requires knowing when to pause. By modeling distinct human interaction styles, the authors created agents that are not just capable, but genuinely collaborative, boosting user satisfaction by over 26%. This suggests a shift from pure automation to adaptive partnership. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.